61A, lecture number 22, Q&A.
The question is about creating attributes inside of a function, which I did in an example from this lecture. It turns out that if you have a function, that function itself can have attributes. Now, right now, it doesn't have an attribute. If I call f on 10, I get nothing because it has no attribute y. But I could give it one. And now when I call f on 10, I get 15. You know, functions can have data associated with them. That's been true for a long time, since we talked about higher order functions in lecture 4, I think. And here we have another example of a function with data associated with it. Basically, what's going on here is that functions are values, they're objects. Objects can have attributes. It turns out in Python that any user-defined function can have arbitrary attributes. And so this is one way of just associating data with the function by storing it as an attribute in the function. And the nice thing here is that it is mutable. So you can kind of change it later. There's no control over who can change it, so that it makes it a little bit too flexible in some cases. But this is an alternative to, for example, using non-local assignment or a higher order function, is that you could just store the data right there as an attribute in the function. Yeah, great question. The question is about space complexity and whether recursion uses up a lot of space, because every time you make a recursive call, you're allocating more space to hold the frame that represents the kind of first frame in the environment for that recursive call. And so if you make 50 recursive calls, then you're creating 50 frames. Yeah, that's exactly right. There is one answer to this that exists in other programming languages, but not in Python, which is that there's like a special case where it turns out you don't need to create a new frame. You could just kind of reuse the old one. Called tail recursion. We'll talk about that. It's an optional topic in a few weeks. But this is just like one particular esoteric point. I guess the main point is that, yes, when you make a bunch of function calls, then you introduce a bunch of frames, and this incurs some space overhead. So if you could avoid it, that's not a bad idea at all. So typically when you'd write when you have just some iterative process, you want to like go through all the elements in something. Then in Python and most other programming languages, the best way to do it is just with a while or for loop and not to write it recursively. Recursion isn't really for that. It can be used for that, but what it's really for is for tree recursion and processing trees or other hierarchical data structures. That's where it's quite helpful. And if you think about those cases, actually the space use tends not to be that large. So in a typical tree recursion, you're going to have a massive amount of computation if you don't memoize, because you're like building out this whole tree of many, many different recursive calls. But the space that you need is only the length of the longest path through that tree. And you could have many more nodes in the tree than you could have the height of the tree. And so for that reason, the space usually isn't the kind of important limiting factor for a tree recursion problem. It's usually time, making all those calls, rather than the amount of space it takes to capture all the active ones at any particular moment. Usually, it depends on the problem.
I mean, 20 years ago, space was a real concern. These days, it's a little bit less of a concern. Memory is cheap. Everybody's got a terabyte of memory. So we worry a little bit less about memory. But you're absolutely right, Mishan, is there are certain recursive functions we have all written that you would never really do recursively. There's no reason not to do them iteratively. It's just more of the exercise of learning recursion.
And if you think about a tree recursion problem like count partitions, where you're kind of making branching calls, there's a way to do this without recursion, but it does use the same amount of space if you do it without recursion. You basically just have to track all the frames explicitly in a list instead of having the interpreter do it for you. So it's not like avoiding recursion tends to help you much there.
And then some problems, so if you watch the lecture on the towers of Hanoi, the solutions are just so much easier recursively. Like to have to think through the iterative solution can be really gnarly. So every once in a while, there's a very clean and elegant recursive solution. Those are the ones I particularly like.
And I guess the final case to talk about is when you're doing something with a tree. That's a common case for recursion. And in that case, like the tree is already there. You've already like used that much memory. So having an extra frame for each node in the tree, it's more, but it's not like a lot more. So it tends not to be a big issue. That was a long answer to a simple question, but
I guess it wasn't that simple. No, it's a great question, Mishan. It's absolutely the right question to ask.
And so if the kind of essence of the question is, should we not use recursion for stuff where we could just use a while loop? Basically, that's a good piece of advice.
Yeah.
Okay, so the question was about the exam prep sections worksheet number 6, which covered object-oriented programming and had the following question on it. Fill in each of the blanks in the code such that the expressions and outputs in the table below are consistent. Okay, so it gives you a bunch of examples. And assume that effects from previous subpart persist to future subparts. I think that's like as we go down here, changes are going to accumulate. So we have a party class which has a guests linked list as its class attribute. Some init that we'll have to work out, some notion of attending. And then we have a costume party, which is a subclass of party that's got its own init. It's going to do something to party's class attribute called guests. And it's going to do something to its own instance attribute. And it's got its own notion of attend, and it's got its own repr method, which I guess is going to be pretty interesting here. So let's take a look at what's going on. When you create a linked list, you create it with 2 arguments, the first element and the rest of the list. If you left this link.empty out and just passed in 1 argument, you get the same thing, because link.empty is the default value for the rest of the list. And link has a repr method which generates an expression that would create an equivalent linked list. Okay, so that's what we see here and here. What we see here is that when you create a party with 1 as its time, and you look up the guests, you end up with a linked list that's got 2 in it. We don't really have a story for why that would be, except that here we have an assignment line that we could use to change party got guests to be something else. Or we could change the instance attribute for guests to be something else. And the tricky thing about this problem is that we don't actually know which one it is yet. Like you can't tell from this expression whether guest is an instance attribute or a class attribute. But since the class attribute is there already, hopefully it's that. Okay. When we call party3 and then .attend, now we have, well, an interesting pattern is emerging, which is that this is 1 more than that, and this is 1 more than that. And then something a little bit crazy happened here. This is not a linked list, but instead, well, it is a linked list, but it doesn't have 3 elements. Instead, it's got 2 elements, where the first one is 4, and the other one is its own list. So if we were writing this in a Python list, this would look like 4 with 2 as the second element. That's what this link4, link2 structure is equivalent to. And how we got here, I guess we don't know yet, but we can take a look at what attend does. So attend does something. And then it returns self.guest is party.guest. Okay. So that must be true, because otherwise we'd just be getting false, and that's not what we're getting. We're getting a linked list. And so it's returning party.guest. So this is an interesting hint. Self.guest is party.guest means that there really is no instance attribute on a party instance. Instead, it must be a class attribute for these two things to be the same thing. So it must be that we're manipulating class attributes here. And we can look at how that happened. We added something to the linked list, and then somehow we got this nested structure, which I guess we're going to have to understand. It's plausible that the elements were added here and that the nested structure was created here. Maybe. This is more of a puzzle than I would expect, but I think we're making some progress. So let's see if we can fill some of this in, and then I'll stop and take questions. So it seems like this has to be that party dot guests is being changed. And how's it being changed? Well, as far as I can tell, we're taking time, adding 1 to it, and putting that in as a new element in this linked list. How do you take an existing linked list and put something new on the front? Well, you call link with a new element on the front, and then keep the rest of the list in there. So the original list becomes the rest of the list. You would write that as party.guests. So this just makes like a linked list of numbers. Every time you call party, then you get like another element. Now, why is it that guests and time are somehow related? I have no idea, but I didn't write this problem, so here we are. Now we have to think about this nested structure. How could it be that after calling party 1 and party 3, we had guests as like a nice linked list that looked like link 4, link 2. And somehow we got an extra link in here. We're going to need an assignment statement in order to do that. I think in order to get from here to here, let's see if I can line these up a little bit better. We have to change the rest of this linked list in order to be a linked list that contains whatever was there before. This is a valid thing to do. Maybe we'll do a Python list version of it in a minute, but let's talk about what it would look like. So this would be like party.guest.rest equals link of, oh, I typed it wrong, party.guests. This particular assignment statement would get us from here to here, because all we did was replace what was in this position with a linked list containing what was in that position. Then, if you evaluate this, you'll find that self.guest is party.guest, so that's true. An and expression will always return the second thing if the first one is true. And so the second thing is party.guests, which means we're returning this whole linked list, and that's what we see. So this is now the value of party.guests. Nothing in the chat yet. People want to ask questions, you can just chime in. Otherwise, I'll keep going.
Here's a question, John. Why is it not party.guest.rest for what's in the link parentheses?
Oh, yeah, I probably should be.
I think that's right. Because if you go down to the,
Yeah, you're right.
I think that's right. Otherwise, the party 7 wouldn't have worked, I think.
Yeah, otherwise we would have had a 4 in here.
Yeah,
and we don't want a 4 in here. We just want the rest of that. All right, thanks.
That's right. Thank you, Raymond.
Okay. what's going on with this costume party? Well, let's take a look. So when you call a costume, you pass in a bow and a tie, which is going to update party.guest.rest somehow, and it's going to update this instance attribute. And then we're going to attend, which calls this. It doesn't necessarily call the party function at all. What it does is it prints a repr string for self.ie. And what came out was nice. Link costume. These both have to have appeared as a result of this print call because attend doesn't return anything. So none of this is due to attend's return value. This all has to be from the print. So when you call repr on selfie, you are invoking the repr method for the class of selfie. So this is not immediately going to invoke the repr method for this value itself, because instead it's just going to invoke, oh, come on, invoke the repr method for whatever this link is that we've created. Now, if this link happens to contain the costume party instance, then we'll get a call to this repr. Man, this is a convoluted one. So we need to construct this value such that we get to print nice right here. I'm going to make a hypothesis, then we'll trace it through and see if we got it right or not. I think the trick is to print nice here to return costume here and to create here a linked list with only one element, and that element is self. Whew, let's see what we've done. I'm going to ignore this line for a while. Just work with what we have. If it's the case that we create a costume with 5 and 6, so far we're ignoring the 5 and the 6. And we're creating an instance attribute, which is a linked list containing just this costume instance. Now, when we invoke attend, we're calling this method, which prints the result of calling repr on selfie, which is a linked list containing the costume. When you create a linked list, when you create the repr string for a linked list, well, what it does is it gets the string that represents each element and puts those into a larger expression. So let's take a look at it. And this is true of all kinds of lists. We happen to write it explicitly. When you want a repr string, here's an example. The way you do it is that you recursively get the repr string for the rest, but you also get the repr string for the first, and then you put those together into an expression. It's like link of whatever the first looks like and whatever the rest looks like. So to get a repr string for this linked list, you need to figure out how to write down the number 1, and you need to figure out how to write down the rest of the list, and then you put them together into one expression. That's what's happening here. Here, we are trying to draw this as a string, which means we have to call repr on self. When we call repr on self, that invokes this repr method, which prints out nice, returns the string costume. That's the string that's representing this costume instance. And then it is the repr method of the link class that puts the word link and the parentheses around whatever I returned right here. And that's not even the end of the question, because apparently there's a part.
There's a whole nother part to it.
Attend again.
This is a good. I have to say, this is a killer question.
Yeah. If the exam prep is difficult, then maybe the exam will seem more reasonable, or maybe not. We'll see. So this is changing what party.attend does in some arbitrary way. I think the easiest way to get this behavior would be to just kind of ignore everything and say, oh, from now on, party.attend just returns this text.
That's really bizarre.
That's one way to hack it, to do what we want.
Yeah, and that actually would be right.
There totally could be another way that involves getting party.guest.rest to be.
No, there's no way. There's no way you're converting the what's the current party for. Yeah, no, that's got to be the way to do it, right, John?
Well, no, there's this opportunity to like reset party.guest.rest to whatever we want. So it was this, but we could rewrite it to have an 8 and a 4 and a 5 in it there.
Yeah, okay.
And then we could like print that out. But in any case, I think this solves the question. Party 7 just does whatever it does. Who cares? Because now whenever you invoke attend, you just get this. Probably not the answer that was intended, but okay. Whew. A really great exercise, I would say, is trying to figure out how some nested structure would be represented as a linked list.
Mm-hmm.
If you have this thing, what's the linked list equivalent? So, let's call this S. What's the T? Well, it's a linked list that starts with 1. The next element is actually another list. And what's the last element? Just a number. Uh-oh. It's never a good sign.
Yeah.
So S looks like that. T looks like some monstrosity, but there is a stir method on linked lists that does something kind of reasonable. Basically, this was designed. Let's look at that. This stir method, which you get when you print something out. Oh, look, this example looks very familiar. This stir method was designed so that it behaves in basically the same way as the built-in lists repr, so that you can kind of look at the correspondence between the two. Now, it's still the case that in order to access stuff in here, accessing something in here, like getting the 2 would look like that. But getting the 2 in here means you have to treat it like a linked list. You have to get the rest, and then you have to get the first, and then that turns out to be a linked list, and so you have to get a number out of that. So still the operations are different because it's a different kind of data structure, but it can represent the same sort of nested stuff that you could if you were just using Python lists.